Good morning, data management enthusiasts. I am away at OFSA with the senior boys basketball team at the moment, so I have recorded some videos so that I can still talk with you about 3.1 that we almost finished on Thursday, but didn't because of the assembly. So I would like to pick back up right here in 3.1 and just recap what I talked about. So I started to talk about expected value, which is essentially the average, or in this case, the weighted average. So what that means is, as we talked about on Thursday, taking an average means you take all your values, add them up, and divide by however many values you have. So that's what this expected value formula is doing, except for the fact that the values of 0, 1, 2, and 3, and don't forget this was the example where we had 3 coins and we were flipping the coins, and we were interested in the number of heads that were tossed in those 3. So you could toss 0 heads, you can toss 1 head, you can toss 2 heads, or you can toss all 3 heads. Tossing 1 or 2 were equally probable. Tossing 0 or 3 were equally probable, but less so. So when we want to calculate the average, I do remember on Thursday we talked about average being the middle. So we would expect our expected value to be right here. This graph is symmetrical. So this point right here would be 1.5, and we can see it graphically that the expected value being the average would be 1.5. But to understand the formula, because you don't always have a graph and it's not always symmetrical, what we want to look at is how do you take an average? Well, you still add up the values and divide by the number of values, but, and here are the values, by the way, x1, x2, x3, x4, x up to n, whatever, however many you have. But the reason we multiply by the probability of x1 is because that weighting of that value indicates the prevalence of that outcome. So if the probability of flipping 0 heads in 3 flips of coins is only 1/8, then we would multiply the outcome of 0 by 1/8, and it wouldn't have as big of an impact as the outcome of flipping 1 or even 2 heads in 3 coins, because the probability of flipping 1 or 2 has a higher probability, 3/8. And we would keep going until we got to our last outcome, which was 3, and we would multiply it by its corresponding probability, which is lower. So this is what we call a weighted average. What we divide by there is the sum of the weights. And as I said on Thursday, it doesn't show up here because the sum of all probabilities, if you are encountering all outcomes, is always 1 or 100%. So that's why you're not seeing that divisor in this equation. Another symbol that means to add things up is this sigma notation, which means you're adding every one of these xpx's. Okay. I did fill this in on Thursday. In a fair game, the expected value is equal to 0, and we're going to talk a lot about that in the future. But let's actually work out the expected value for these coins using this formula. The outcome of 0, it has a probability of 1/8. The outcome of having 1 head in the flip of 3 coins is 3/8. Same with the outcome of having 2 out of the 3 being heads, also 3/8. But the probability of flipping all 3 heads is lower. It's only 1/8. And if you want to really stick to the calculation of an average, then we would divide by the the total weights. So 1/8 plus 3/8 plus 3/8 plus 1/8 is 8/8. That's 1. That's why we divide by 1. You don't have to show that. I'm just trying to convince you that this formula is really just an average. Okay, so when we work this out, of course, that disappears. We get 3/8 plus 6/8 plus 3/8, which is 12/8, or as a decimal, 1.5, which is what we said we were going to find by looking for the average graphically in a symmetrical graph. So hopefully you're convinced either graphically or algebraically or both that expected value is simply the average, or weighted average in this case. Okay, let's flip over. Another word for uniform is constant. And the outcomes of a uniform probability distribution all have the same probability. A uniform probability distribution. This one here is not a uniform probability distribution. An example of something that has a uniform probability distribution is rolling a die. You have a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling a 2, a 1 in 6 chance of rolling a 3, etc. 1 in 6 for each of the 6 outcomes. That would be considered uniform probability, equally likely. Each side of that die is equally likely to turn up every single time you roll it. Okay. Therefore, if there are n number of possible outcomes in an experiment, then probability of that outcome is 1 over n. So in the case of a die, it would be 1 over 6, and they're all 1 over 6. So that's what uniform probability distribution would look like. And if you graph it, of course, all those bars in the bar graph are going to be equal height. So let's look at example 4. In a lottery, 1.2 million tickets are sold at $1.25 each. What is the expected value of each ticket? Okay. Well, the prizes have different values. You can win $1 million, you could win $100,000, or you could win $10,000. There's only one prize of $1 million, only one prize of $100,000, but there's 3 prizes that are $10,000. So what we want to do, first of all, is recognize we're looking for our expected value. That's the notation. Expected value is the sum of x, px. X is the outcome, px is the probability of it. So let's come up with those values. I'm going to extend this chart. So let's find the probability. Okay. The probability of winning the one and only $1 million prize, given the fact that 1.2 million tickets were sold, and we're assuming this lottery is just a random draw lottery. Oh, I'm kind of crooked here. Sorry. Okay. So if you have one of the $1.2 million tickets, then you have 1 in 1.2 million chance of winning the $1 million prize. Same with the $100,000 prize. There's only one of those, so only one person in that 1.2 million people is going to win $100,000. However, there's 3 prizes of 10,000, so you have a 3 in 1,200,000 chance of winning the $10,000 prize. Okay. Oops. Sorry, one sec. Extending my table a little more. because now we've got the PX column. Now what we would like is the XPX column. So I would like to multiply my X by my PX. So the value of this prize is $1 million times its probability would be 1 million over 1.2 million. XPX for the 100,000 prize. Now I'm just multiplying, this is X of course. I'm just multiplying my X by my PX. So I would have 100,000 over 1.2 million. And for the final, we would have 30,000 over 1,200,000. Okay, so there is my XPX. I'm going to move this out of the way. Move it a little lower so we can still look at it. The sum of XPX is what I need for expected value. So I'm going to add a box at the bottom where I can add all these up. Well, lucky for me, they have a common denominator of 1.2 million already, so I just need to add the numerators. 1 million plus 100,000 plus 30,000 is 1,130,000. Okay, so there's my sum of XPX. XPX were all of these, and in this box, I just added that column. So my expected value is that, but as a decimal is 0.94. So what does that mean? All right, this is really important, and it's going to mean a lot to you come game time. So imagine these 1.2 million ticket holders. You know that they paid $1.25 for their ticket. Because we know expected value is an average, what this is telling us is how much each ticket purchaser would have to pay so that if all the prize money were spread out evenly among everyone, the lottery company would break even. They would give out all their prize money and they would have nothing left over. Okay. However, these ticket holders did not pay 94 cents for their tickets. They paid $1.25. So no, this is not a fair game. The difference between $1.25 and 94 cents is kept by the lottery company. Okay, so let's write, because the expected value is not equal to 0, this is not a fair game. Remember, we said a fair game is when expected value is equal to 0. So this is not a fair game. And the reason it's not a fair game is because $1.25 minus 94 cents is 31 cents. Crooked again. So that's not 0, and the lottery company is keeping 31 cents of all ticket sales. Now, it's true that not every person who buys a ticket is getting some prize money. They're not. It's not how it works. However, this would show us what they would have to pay to generate equal prize money for everybody and generate no revenue or profit for the lottery company. Okay, So that is it for that one. And we parted on Thursday. I think I said maybe give a couple of these a try, but maybe you didn't. Maybe you didn't get very far because you really needed to hear the rest about expected value. So why don't I leave it at that and let you try the homework.